All right, so today's lecture is basically going to be building Bitcoin from the ground up. After today, you should be able to explain how Bitcoin works to a friend. It's going to be kind of a high-level overview, and we really want to flesh out some of the details. So I'm going to just do a quick intro of the technology and some terminology, then spend about 30 slides or so doing a buildup of putting Bitcoin together piece by piece and seeing how all the different pieces play together. Then we're going to tie that into the actual implementation details of Bitcoin, talk about mining a little bit, and then if we have some extra time, I'll get to talk about some Merkle trees and forking, which are very important for Bitcoin. Okay, so Bitcoin is always deemed as like the first cryptocurrency. It's kind of what started everything. And cryptocurrency, you can loosely define as some digital currency that is tied together using computer science, economics, and cryptography. In general, this is a very interdisciplinary field. And whenever we talk about blockchain, blockchain is simply the technology that is underlying Bitcoin. And it's the key data structure that allows Bitcoin to reach consensus in a distributed way, in a decentralized way. So some of the community terminology that you'll hear about, whenever you hear crypto or cryptocurrency, it's usually talking about the more technical aspects, usually talking about public blockchains, so basically blockchains where anyone can participate, like Bitcoin or Ethereum. Whenever you hear private blockchains or permission ledgers, or sometimes just the word blockchain, this is usually what banks and large financial institutions are referring to. They're interested in blockchains where every participant in the network is known beforehand, and only certain people have right access. And then, as an umbrella term, you'll sometimes just hear distributed tech or decentralized tech. So let's talk a little bit about Bitcoin and consensus. As you know, Bitcoin was created by Satoshi Nakamoto in 2009. This was basically an anonymous pseudonym. We still don't know who he is. He wrote a paper, published it, started Bitcoin, and participated in the community for a few years, and then he just dropped off of face of the earth. So could be he, she, they, a group of people, we're not sure. But what he essentially did was he created the first ever decentralized trustless system for transactions. Where you don't have to go through any intermediary or any entity to be able to agree on what the transaction history is. And it's democratizing in a sense because to have financial access or access to financial services, all you need is a computer and an internet connection and running the Bitcoin software. And how he created Bitcoin was he solved something known as the double spending problem. So it's basically in a digital realm where it's really easy to replicate things, replicate files, replicate whatever. How do you prevent someone from spending the same asset twice? How do you? And this is a very fundamental innovation that enabled everything else in blockchain tech. And his solution to this was introducing the data structure of blockchain and something known as a proof of work. So in the next 30 slides or so, I'm going to build up Bitcoin piece by piece. This is where you should really try to pay attention. And hopefully at the end of this, you're going to have that click moment, like, finally, I understand Bitcoin. All right, so let's start with the basic notion of a transaction. In this version, if Alice wants to send a Bitcoin to Bob, she just says, I, Alice, am giving Bob 1 Bitcoin. And Alice's signature ensures that she can't just go back and deny sending Bob that Bitcoin. And remember, in this model, there's no trusted bank to keep a record of anything. So next, Alice is going to send her transaction to everyone running the Bitcoin software. Now, everyone knows that Bob has 1 more Bitcoin and Alice has 1 less. But there's a major flaw of this first version. Alice could keep sending the transaction 5 times. What would this mean? Would it mean that Bob now has 5 copies of the same Bitcoin or 5 different Bitcoin? So the next version needs to address this. So we can solve this naive issue of double spending by introducing serial numbers to make these Bitcoins uniquely identifiable. Now if Alice wants to send a Bitcoin to Bob, she can say, Alice, I'm sending Bitcoin to Bob with serial number 8732 signed by Alice. This way, she can only spend each Bitcoin once. But the thing is, where do these serial numbers come from? And how do we manage who owns which Bitcoins? With serial numbers, Bob can make sure that Alice doesn't send him the same Bitcoin twice. But how can you be sure that the Bitcoin belonged to her in the first place? So this is typically where we'll bring in some, central bank or some financial intermediary, basically a trusted source of these serial numbers. This bank is going to provide the serial numbers for the Bitcoins, keep track of who owns which Bitcoins, and ensure that every transaction is legitimate. So now when Alice sends her transaction to Bob, Bob can go to the central bank and check to make sure that this transaction is legitimate, the Bitcoin belonged to her, and that it is unique. Question?
Are transactions made instantly?
In this model, you can assume that is, for now, yeah. So there's a big problem with this, actually. To solve the issue of duplication and double spending, but we kind of defeated the whole purpose of Bitcoin by making it centralized. So let's see if we can bring back this decentralized nature. So how we do this is we make everyone the bank. Now everyone has a complete record of every transaction that's ever occurred. And in Bitcoin, this is called the blockchain. That's right. All right. So now when Alice sends her transaction to Bob, he can check his copy of the blockchain to be ensured that the Bitcoin actually belonged to Alice. Now, if that works out, he's going to announce the transaction to the world, and everyone will update their copy of the blockchain. But there's a problem. What if Alice sends her transaction to Bob and Charlie simultaneously? Both will check their copy of the blockchain, find that the Bitcoin belonged to Alice in the first place, accept the transaction, and announce it to the world. How are these other nodes, David, Eve, whatever, going to update their copies of the blockchain? Obviously, both Bob and Charlie can't own the same Bitcoin, so we have a problem. So we can begin to solve this problem by giving everyone the power to verify a transaction. Now when Alice sends her transaction to Bob, he shouldn't try to verify this transaction alone. Rather, he should broadcast the possible transaction to the entire network of peers and ask them to help verify. And if enough of these users verify the transaction, Bob can accept the Bitcoin and everyone will update their copy of the blockchain. Question?
So let's assume that Alice sends Bitcoin to both Bob and Charlie or whoever she is, and D sends this request to everyone asking them to verify the Bitcoin, and so does Charlie.
Yeah.
What if both of them get different numbers?
Yeah, so the key thing here is that it's a possible transaction and that it's not immediate. So in this case, if Alice were to send it to both Bob and Charlie ask the rest of the network, and the rest of the network will see, I'm getting a request from Bob, getting a request from Charlie. They're trying to spend the same Bitcoin, so there's a problem. We're going to reject one of them. Yeah.
Can Charlie choose to not ask other people in the network to verify?
Yeah, but then that would expose him to a vulnerability of being double spent on, which is not something he would want. Yeah. Okay. So this way, if Alice tries to double spend on Bob and Charlie, the other users will notice and reject the transactions. However, there's a problem with this approach. Alice could double spend on Bob and Charlie by taking over the entire Bitcoin network. She could use an automated system to set up a very large amount of identities, and it's just basically Alice, Bob, Alice, 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 Charlie, Alice. So now when she double spends and Bob and Charlie ask the network to verify the transactions, Alice's many identities swamp the network and tell both Bob and Charlie that, hey, this transaction is fine, you should accept the Bitcoin. So now she's essentially fooled them into taking the same Bitcoin. And the proper term for this in general, and you'll hear this a lot in the course, is a Sybil attack. It is basically where you create a lot of fake identities to try to subvert some system, crypto system, or whatnot. So we can begin to solve this Sybil attack issue of double spending by implementing something called a proof of work. Now, in a proof of work system, when Alice wants to give Bob some Bitcoin, she announces her transaction as a message to the entire network. And as other users receive Alice's transaction message, they add it to a list of pending transactions that they've been told about but haven't yet verified. And note that any user can maintain their own list of pending transactions. So this might be David's list of pending transactions, which will look different from Charlie's. Now, if David wants to verify these pending transactions in this proof of work system, he needs to do three things. First, he's going to check his copy of the blockchain to ensure that the transactions are legitimate. The Bitcoins haven't been spent before. Second, he needs to use computational power from his computer to solve some very hard mathematical puzzle. And third, he's going to announce this block of transactions to the network. So before we take a closer look, remember that if David doesn't want to verify any transactions, he actually doesn't have to. He can just let all the other users in the Bitcoin network verify transactions. So you're probably wondering, why does David's computer have to solve this math puzzle? This is a really important question. By requiring David's computer to solve this math puzzle, we're actually solving the problem of double spending. So let's take a look at that example again. So by setting up a large number of identities on the network, Alice can fool Bob and Charlie. We want to make it really costly for Alice to double spend, but it's really difficult to identify a dishonest actor before they act. So what do? We simply make it costly for anyone to verify transactions. And in Bitcoin, that cost is the proof of work. So you can think of the proof of work as a competition to verify transactions. If your computer solves the math puzzle before the other computers on the network, you'll get to verify this block of pending transactions, and you'll receive some Bitcoin as a reward. Proof of work prevents bad actors like Alice from double spending because it puts them in competition with everyone else in the network trying to verify transactions. And so long as most of the computing power on the network is controlled by honest people, malicious actors like Alice will have a hard time doing things like double spending. Question?
Are you allowed to freely look at other people's transaction lists?
Are we allowed to freely look at other people's transaction lists? In Bitcoin, you are, yes. Yeah.
Isn't your transaction list the same as someone else's transaction list? Because you have a list of all the transactions that are happening all across the world or in your own block, and you want to verify each one, right?
Yeah.
So everyone has the same list.
Yeah, so the question was, does everyone have the same list of pending transactions? Generally, yes. It might differ. This is just coming down to implementation details. Like, if you don't want to include this giant transaction in your block as a miner, then you don't have to. You have choice over what you include and what you don't. Yeah.
Can you make transactions across blocks?
Can we make transactions across blocks? We can make transactions that link to each other between blocks. Yeah, but there won't be a single transaction that's in multiple blocks. Yeah. Okay, so kind of summarizing the little buildup that we did. First, we introduced, the basic notion of this piece of paper, this, transaction that's signed, so you can't go back and say that I didn't spend this Bitcoin. Then, solving the naive version of double spending, we introduced serial numbers, and then we decentralized the system by introducing a blockchain where everyone has the complete record of transactions. Now, we have everyone verify transactions to mitigate the naive double spending attack. And then in a proof of work system where you try to double spend in a Sybil attack, this is where you can finally totally solve the problem of double spending. All right, so question, yeah?
I think I'm kind of lost about how the person who verifies the transaction gets Bitcoin in return, but it's a competition. I thought that everyone in the network is verifying the transaction. Did I misunderstand how it works?
Yeah. So I think I could have been more clear there. So the question was basically who gets the reward? Basically, isn't everyone verifying this transaction? It's the first person who solves the math puzzle that is able to verify this whole block of transactions for the entire network. Yeah.
And then what happens is once they propagate their solution to everyone, because everyone wants to start working on the next block, before they're able to do that, they have to check the work of the whoever won. They have to make sure they did everything correct, because then Max will get into it why like the previous block header is in the next block.
Yeah. Question.
So who generates the puzzle and who know the answer?
Yeah, so I'll be talking a little bit about the puzzle in the later slides. The short answer is that the puzzle is deterministically based off of the current network state. Yeah. So, question?
So when you find the solution to the block, what happens when someone does double spend?
What happens when someone? Okay, so the question was when you find the solution to the block, what happens when people try to do a double spend? So the assumption here is that the majority of computational power in the network is controlled by honest nodes, and they're not going to include double spent transactions. Actually, it would be rendered invalid by all the clients. How about this? After I fill out some more of the implementation details, we'll come back and like answer a lot more questions, because I feel like answering them now will only introduce confusion by putting it in the wrong order. So, yeah. So let's tie this, abstract concept of transactions, money, to the actual implementation of Bitcoin. So in Bitcoin, you're actually how you own the money is you're sending money between pseudonyms, and in pseudonyms, it's just in Bitcoin, your pseudonym is just your Bitcoin address, which is just the hash of your public key, and it builds on several cryptographic primitives. First, you need some kind of a digital signature scheme. Basically means you need some kind of public key, private key pair. So for those of us not as familiar with cryptography, you can think of it like an email address and a password. Like if I want to receive an email, I need to give it to someone, and to access those emails, I use my password. You also need a one-way cryptographic hash function, and in Bitcoin, that hash function is SHA-56. So the key property of a cryptographic hash function is that given some input, it could be arbitrarily large, some large blob of data, you run it through this function and it's going to deterministically come to the same output, the same fixed size output every time. And the key thing is that given this output, it's really hard to find the input that would have produced this output. In other words, it's very hard to invert the hash function. Some other properties of hash functions that will be, very useful or even necessary are that, like, given some, input and output, it's hard to find another input that is going to yield the same output. And likewise, like, a very tiny change in the input is going to result in a completely different output. We'll see later in the lectures, through this lecture and all the other lectures, why this is very important. Hold on. Your phone is ringing. All right. So, Bitcoin is, whenever you're owning Bitcoin, you're basically like hiding it in the very large number of public keys. And as a user, you can generate arbitrarily many key pairs. So that's an example address. You can look at all the bits of entropy in there. That's also my address if you want to send me some money. And so there's 2 to the 160th possible addresses. To kind of like put this number into perspective, imagine every single grain of sand on Earth, every desert, every ocean, all across like the beaches of the entire world. Now imagine that for every grain of sand on Earth, there's another Earth, which is with its own sets of grains of sand. And that set of grains of sand is the number of possible Bitcoin addresses. So this is why we think it's fair to assume that, like, just by randomly generating some, public-private key pair, you're not going to collide with someone else's Bitcoin and be able to steal their Bitcoin, or they'll be able to steal your Bitcoin. Yeah. Okay, and Bitcoin exists as software. I think this is kind of obvious. And whenever you own Bitcoin, you need to download some kind of wallet, and that's how you conduct your transactions. So for example, right here is the Coinbase interface. The top part is the receive money interface. It's just your Bitcoin address, sometimes accompanied with a QR code for easy scanning. And the send funds is you just enter in a Bitcoin address, an amount, press send. Grandma can do it. And whenever you're making a transaction, like I said, you broadcast this transaction to the network where the miners will verify it. Now, transactions in Bitcoin are actually not what most people might think. Most people think of a financial system as like, I have an account with like, this balance of coins in it. But it's not like when you're spending Bitcoin, you're just subtracting from that account. You're actually spending from previous transactions. So to elaborate on that, a transaction is basically a mapping from inputs to outputs. And at each input is an address and an amount. And at each output, it's also an address and an amount. So in the typical example of, say, I have 1 Bitcoin, and I want to go to a coffee shop to buy a coffee that's worth 0.05 Bitcoin. What I would do is I'd construct a transaction that has a 1 Bitcoin input, a 0.05 Bitcoin output to the coffee shop, and 0.95 back to myself. So the reason why we want to split this into 0.05 and 0.95 is because that 1 Bitcoin can only be spent once. So this is why we need something like a change address to bring it back to ourselves. And to introduce maybe even a little bit more complexity here, say I wanted to include a fee in this transaction to the coffee shop. I want to reward the miners like 0.01 for including my transaction. The new transaction I would construct would be 1 Bitcoin input, 0.05 to the coffee shop, 0.94 back to myself. And then the 0.01 will be implicitly calculated as the difference between the sum of the inputs and the sum of the outputs. And this is what the miners will collect as the transaction fee. So questions here? Yeah.
How are the parts of the Bitcoin identified? Do they have serial numbers themselves? Because if I split it up, how do you decide?
Yeah, so each output, so you can see we have chains of transactions where outputs link to future inputs. Each output is a unique, basically you're spending from unique outputs, and that's how it's uniquely identified. Yeah.
So in fact, each Bitcoin doesn't really have a serial number. It's really each previous transaction has a serial number.
Yeah.
So you're never actually spending
each previous transaction output. Yeah,
So
so you can actually spend the parts of a transaction independently. If you have 3 outputs, you can spend them one at a time. Yeah, question?
So since you're saying that people can basically kind of give a little donation to the miners, does that mean there's not a fixed work rate essentially for miners? It varies depending on whoever donated to you essentially?
Yeah, so how about I'll cover that in a few slides. Yeah, question?
So is this more secure than having a bank account?
It depends. It depends on who you trust to manage the private key. If you trust yourself, then I guess it's more secure, but I wouldn't trust myself. Yeah. Yeah. Question?
What was the question she asked?
Oh, she was the question she asked was, is this more secure than bank account? Yeah.
I would say yes, because a bank account, you can't really trust the bank. Not just purely because of super libertarian, fuck the banks. Also because banks can be hacked, right? Yeah. If a bank is hacked, your money's gone.
Well, the bank can also be reversed. So let's not go in that direction right now. Yeah. Okay, so kind of filling out more of the infrastructure. Blocks are basically an ordered bunch of transactions. I very specifically say ordered bunch because sometimes the transactions can depend on each other. In other words, one transaction spends from a previous transaction, and they might actually be in the same block. So you need to order it correctly. Otherwise, the transactions will become invalid. And the key thing about these blocks is that it timestamps these transactions, and this whole block is completely immutable. So that if you modify any part of the block, it'll become an invalid block. So we'll see more of why that is the case in future slides as well. And each block has a reference to a previous block, so that is how we form the blockchain. Right here is a screenshot of blockchain.info. Blockchain.info is a block explorer, so-called, where you can basically look up any address, look up any transaction, and kind of see the details. So we're looking at a transaction right now with a giant 44,000 Bitcoin input and a bunch of outputs. And you can see this kind of illustrates like most of these outputs have been spent, but if they wanted to spend more, they can spend from this unspent output. And it also contains some crucial information like the total sum of inputs, total outputs, fees, etc. Yeah, question?
What is that in dollars?
What is what?
That in dollars?
I mean, 38,000 multiplied by 900, or 1,000 now. Yeah, man. Like, yeah, when I last delivered this lecture, the price was like $960. Yeah.
The last was like 2 days ago.
Yeah, 2 days ago. Okay, so kind of like what I've been saying about in Bitcoin, you don't have an account with like a balance that you're just subtracting from. You're spending from unspent transaction outputs, or UTXOs. This is a term that you'll hear a lot in this space. And you can think of the UTXO set as the global set of unspent Bitcoins. And this is how you measure how many Bitcoins there are in the ecosystem. And one way to illustrate is this, like you say like, I'm spending this Bitcoin, I'm not spending a Bitcoin. I'm spending this one very particular Bitcoin. And this is actually analogous to the rye stones of the Yap civilization. So basically they had these giant stones spread across the island, probably a little bit too big to put in your pocket and use as currency the way you typically would. But whenever they needed to make transactions, they wouldn't obviously physically move the stones around. They would just have an agreement on the change of ownership. So if I needed to buy like a cottage or something, whatever you bought on that island, I would just announce to everyone else. Like both parties would announce to other people on the island, like, oh hey, Bob owns this rye stone now instead of Alice. So this is analogous to how like things are done in Bitcoin. Like change the ownership of specific Bitcoin is spread across the network. Question?
How do these block rewards come in? Whatever 12 Bitcoin, how would they come into this trade?
Yeah, the question was how block rewards come into this. That's actually in the next few slides. So, okay, so some quick notes on proof of work and mining in general. Proof of work, as we know, is the solution to the double spending problem. And it's an example of something known as a Byzantine consensus algorithm. So if you study decentralized systems a little bit more, Byzantine consensus algorithms are algorithms that tolerate the toughest class of failures, where nodes in a network will actively try to like subvert other nodes by like sending false messages, maybe sending different messages to different halves of the network, or not participating at all. They can do anything to try to prevent the network from coming to consensus. And proof of work is one of a plethora of consensus algorithms. There's other things you'll hear about later on in the course, like proof of stake. And in general, private blockchains, the ones that financial institutions are interested in, they usually use alternative algorithms, but these tend not to be completely trustless. So the typical scheme is where there's like 15 banks, and the banks don't completely trust each other, but they trust maybe 10 out of the 15 other banks. And at each block, all of the banks sign, okay, this block is okay, this block is okay, and proceed on the blockchain that way. And you can think of mining as like, three different things. You can think of it as a minting mechanism for ensuring Bitcoins are distributed in a fair way. So why don't we use like IP addresses or something, right? Because of a Sybil attack. It's very easy to just obtain a large amount of IP addresses, and thus you've subverted the system. You can also think of mining as an incentive for people to help secure the network, for miners to donate their computational power. And it's a key component that allows you to reach distributed consensus. So filling out that flow a little bit more about finding blocks, including transactions. Once you find the proof of work, the term for it is like you found a block. Like up to that point, your block had been incomplete, but now you found the block, and it's this immutable, like solved piece of data that you can add to the blockchain. And the miner who finds this block is allowed to add a special transaction to it called a Coinbase transaction, which rewards them with 12.5 Bitcoin. After they find this block, the solution, they broadcast this block to the rest of the network, and the other nodes in the network will verify this solution, and then add it to their own copy of the blockchain. So some of the timeline and stats, this happens roughly every 10 minutes or so, and I say roughly because it's on average every 10 minutes or so. How they make it on average every 10 minutes is they actually adjust the difficulty of the math problem that these miners are solving, so that on average it takes the entire network 10 minutes to solve each math problem. And the difficulty of this problem is adjusted every 2 weeks so that we can have like a consistent creation rate of Bitcoin. Every 4 years, the block reward halves. So this implies that Bitcoin is actually a deflationary currency that is in limited supply and will have the full set of Bitcoins produced by the year 2140. And some other important implementation details. Each block can only contain 1 megabyte worth of transactions. So this is where the fees really come in. That means there's limited space for transactions in the Bitcoin network because each transaction is some like blob of bytes. There's inputs, outputs, addresses, signatures. They all need to be a part of the transaction, and it costs money to include this. So when miners are listening for transactions, they're actually prioritizing the transactions that they'll put into the block by the highest ratio of fee per data byte. So this will allow them to maximize the profit that they get in their block once they've solved it. So there's about 15.2 million Bitcoins currently in circulation. Price is not 920 per coin, it's 1,000 now. But yeah. Yeah. Oh, okay, 16.1. Okay, that's outdated too. Question.
So by 2140, should people just start pulling out their money from Bitcoin?
No. So the question was, by 2140, should people start pulling out their money from Bitcoin? No, it just means that there's a fixed supply of Bitcoin. It just means that it's not inflationary anymore. Yeah. Question.
So like in 2140, when all the Bitcoins have been produced and distributed, like the demand for Bitcoin will obviously increase.
Yeah, I guess you could put it that way.
Yeah, so if the demand increases, the price will also increase, right? So how can you say it's not inflationary?
Oh, inflationary refers to money supply. So if 21 million were to continue increasing, then that would be inflation. The price of the Bitcoin as measured against other assets is not strictly a measure of inflation. Yeah. Okay. So now we can talk a little bit about the actual mining problem. How are we on time? Let me see. All right. So when you're mining Bitcoin, you're actually taking these 3 components and you're hashing them together. So first, you have something known as a Merkle root. For now, you can just think of the Merkle root as a summary of the transactions in the block. Think of it as a summary in that if you changed the transactions even a tiny bit, then this Merkle root would become invalid. So it's tamper evident, in other words. We'll describe that in more detail in the Merkle tree slides at the end. You have the Merkle root, and you take a hash of the previous block. So this makes each block depend on the previous block, and you have a nonce. And this nonce is essentially the solution that you're looking for. Nonce stands for number of once, and what you're doing when you're trying to solve this math problem is you're taking the Merkle root, the hash of the previous block, and the nonce, you're concatenating them together. Then you're running this through the function SHA-56 to try to find an output that has a prerequisite number of zeros. And that number of zeros is determined by the difficulty in the network. So essentially what you're doing is like, you're taking this nonce, you're repeatedly incrementing it, and repeatedly checking this hash to see if it satisfies the solution. And once you can find that combination of Merkle root, previous block hash, and nonce that has this requisite number of zeros, then you found a valid block, and you can broadcast this block to the rest of the network. Questions?
What's the point of broadcasting for the rest of the network? I mean, like, I'm sure other people will discover blocks too. So you want to solve the problem rather than broadcast it on the network. Right? What do you mean broadcast?
Yeah, so the question was like, what's the point of broadcasting the block to the rest of the network? Well, like once you found this block, you have your 12.5 Bitcoin reward. If you don't tell other people that you solved this block, then you're not going to get that reward. And the longer you wait to tell people, the higher likelihood the rest of the network might have found a block, and they get the reward instead of you. So this is why you need to broadcast the block. Question?
So blocks are made every 10 minutes? Is that what you said?
Yeah, so the question is, are blocks made every 10 minutes? It's on average every 10 minutes.
So that means there are even more transactions being made every 10 minutes.
Yes, yes. Question?
So who agrees is 12.5 Bitcoin as a worth?
Yeah, so the question was, who agrees that it's 12.5 Bitcoin worth? This is actually part of the parameters of the network. When we first started Bitcoin, I think it was like 50 Bitcoin per block. And then every 4 years it halves. So, yeah. Other questions? Yeah.
Are these rewards going into another block or contributing to it? How does that work?
Oh, the mining rewards? So the mining reward is given to the miner who found the block. And then whoever the miner spends it or distributes beyond that is like, up to the miner. Yeah. Question?
When miners spend, they have in the blockchain mine the transaction fees and mining reward. Is that considered one UTXO all unspent transaction output all in itself?
So you said there's a mining fee and
The transaction fees for all of the transactions contained in the block and the block reward.
yeah, okay. So his question was like, do the transaction fees and the block reward constitute its own UTXO that you're spending from? The answer is that like the fees you actually get in your Coinbase transaction. So the fees were calculated implicitly from all the transactions included in this block, and then you just get it in your Coinbase transaction. Yeah. Okay. Question?
Yes, what about the block reward? 12.5 Bitcoin. How do they, are they UTXO as well, just 12.5? What did I mean, how are they connected? Because they just are created out of nowhere.
Yeah, so that is where the Bitcoin is basically created out of nowhere. Like there would have been no input to that transaction. Basically, it's just a special output that you can spend from the Coinbase.
So you can't trade the Bitcoin because there's nothing.
Yeah, exactly. It was newly, freshly minted Bitcoin. Yeah. Question?
To read a previous block, you have to solve another map.
To what?
So like, let's say you want to go backwards in blockchain.
Yeah.
You have to like break the code again to go backwards.
You wouldn't want to go backwards because that means you're going back to old transaction history, which might become invalid after the
I think
new
she's
block.
asking if you want to verify a block, do you have to resolve the math problem?
Yeah, so the question is, if you want to verify the block, do you have to resolve the math problem? Verification is very fast because all you have to do is you take the Merkle root, the hash of the previous block, and the nonce, hash that together, and you just check that it has a prerequisite number of zeros. The time-consuming part is having to hash that billions of times before you find a solution. But checking it is very easy and fast. Yeah.
So I remember you said that the size of a block was 1 megabyte. But what's the geographic size of a block? I mean, like, so can I be part of a block and make transactions within the block which spans both America and Russia?
Yeah. So the question was like, what's the kind of like the geographic properties of a block? And yes, you can make transactions between any country. Like Bitcoin is the borderless currency, and one of its big sells is that you can send $10 million worth of Bitcoin to anywhere in the world for a cost of 12 cents.
I think there was a little bit confusion. Like blocks aren't like any geographical based entity. Blocks just are like periods of time. Like it's all the transactions that happened in the last 10 minutes.
Blocks are basically a set of data bytes on your computer, on your hard drive.
So building on that question actually, so what what determines which block my transaction goes to? Because I'm sure like there are a million blocks out there.
Yeah.
If I make a transaction like at this given point in time, like would it go to Russia? Would it go like stay in America? Would it go to India?
Yeah, so the question was like, what determines which block your transaction is included in? Like, is it in any country? No, that's not true. There's nodes in the network, and the entire network will agree that, okay, this transaction was included in this one block. So it's not, there's no notion of like geography. It's basically like you put out your pending transactions, miners are listening for this, and once they solve the proof of work, then your transaction will have been included in that block.
You only work on the block that's at the like highest depth.
Yeah.
Like once there's a new block on top of an old one, no one touches the old block. That's like there for like the rest of the time, and for the most part, no one's ever going to touch that.
Hold on, I'm going to speed through some slides to make sure you guys get the adequate material for today. And then I'll keep on taking questions right after. One of the major assumptions of Bitcoin is that no more than 51% of the network is dishonest. And by 51%, I mean 51% of the computational power. Because if you think of it this way, if you have the majority of the computational power, that means you're going to be able to solve these math problems faster than anyone else. Therefore, you'll solve blocks faster than anyone else. Therefore, you will always produce the longest blockchain. And that's why we assume that the longest blockchain is the correct history of transactions. And so like if someone in the network had only 10% of the mining power and they tried to like fork the network or like try to double spend, do something like that, eventually their chain will become invalid because they will not be able to catch up to the main chain of honest miners. And a 51% attack is essentially an attempt to take over Bitcoin by acquiring the majority of the computational power. Huh? It is possible, but I don't know how plausible it is, because like here you can see the hash rate of Bitcoin mining. So this is measured in hashes per second. So like, what is a hash? I mean, a hash is just running SHA-256 once. And down there, that is 1 exahash. So like, you have your normal unit, kilo, mega, giga, tera, peta, and then exa. And as of this point right here, the hashing power of the Bitcoin network was greater than that of the world's 500 largest or most powerful supercomputers combined. And that was like a year ago. And since then, the hash rate of Bitcoin has tripled. So we're at 3.3 exahash right now. So essentially, we've built the most powerful computer in the world, but the only thing you can do is SHA-256. Yeah. Okay, so talking a little bit about forking and consensus updates. Whenever you need to make an upgrade to the Bitcoin network, sometimes the new rules that you implement, for coming to consensus, will be incompatible with the old rules that you have. And this is called, a fork. So there's two types of fork. The first type is a hard fork, where you have the new version and you have the old version, and both versions are completely incompatible with each other. So you might have a situation where part of the network splits into this new chain, and part of the network stays on the old chain. And if these people on the old chain don't all switch over to the new network, and there's enough community backing this old chain, it might actually just result in two chains, like two separate networks. As we'll see, this actually happened with Ethereum, where if the Ethereum network literally split into two, called Ethereum and Ethereum Classic, because people didn't want to go onto the new chain. Now, in a soft fork, what you do is you create a new chain that is still valid under the old rules, but the new chain, the old chain is invalid, or what is it? Let's see, you create a new chain that's, a new chain that's valid under the old rules, but for the old chain, the new chain might not be, no. Sorry, I'm getting all confused here. But the old chain will not be valid for the new chain. Let me say that again, just so that we're not confused. So in a soft fork, when you create a new chain that is compatible with the old rules, but these old rules will violate the new rules sometimes. And what happens is that like once people switch to this new chain, there's a chance basically all these blocks are going to be considered invalid by the new chain, and these people continuing on the old chain are going to be like, what's happening? Like, why aren't my transactions going through? So essentially, you're forcing all the people on the old chain to switch to this new chain. Otherwise, they won't have access to the Bitcoin network. And this is generally considered safer because there's no chance of diverging into two chains. You kind of force everyone to go onto the new chain. One more slide. All right, so Merkle trees are basically the very fundamental data structure in a Bitcoin block, and it's what allows these blocks to be immutable. So I've said that you can think of these transactions as data bytes, right? With inputs, outputs, addresses, signatures, whatever. You can run this transaction data through a hash function to receive a bunch of hashes of your transactions. And you do this for every single transaction in the block. Now what you can do is you hash these hashes together in a binary tree structure until you get to this root hash. And this root hash is what we call the Merkle root. And why we say that this is a summary of all transactions is that, say, I were to tamper with transaction 2 right here, and saying like, oh, instead of getting like 1 Bitcoin, I got 2 Bitcoin. Well, the hash of that transaction would change, which would change this intermediate hash right here, which will change this root hash. And once you change this root hash, it would make this block invalid because the hash of these three things together will no longer have the requisite number of zeros. So this is how you can make these blockchains tamper evident. And by including the hash of the previous block in each consecutive block, you're essentially containing the state of the entire previous chain into this new chain. So that if I were to go back and say change something in this block, then these 2 blocks would be invalid because the Merkle root changed, which made this previous hash change, which made this previous hash change, and it's no longer a valid block. I think that's it for today. For next time, we'll be covering cryptography and wallets. If you haven't joined Piazza yet, please do. We have some required readings. I'll stick around if you have some questions. Make sure you fill out attendance if you haven't. All right, thanks.